This lecture is about designing and presenting experiments. Our objectives are to be able to recognize the elements of good experimental design and why they're important, explain how the design of an experiment may lead to specific systematic and random errors, and if you're not sure what systematic and random errors are, try an earlier lecture about measurement uncertainty. Third objective, pose different kinds of testable questions, and finally select an appropriate graph based on your testable question. And we'll see what that looks like in just a bit. The first thing we want to define is what's called a testable question. And this is a question that states what we want to know in terms of what we can measure. Measurement is the key word. If our question isn't posed in a way that specifies what it is we're actually going to measure, it's not actually a testable question. I want to know about how fast I get to work is not a testable question. It's not even a question. If I said I want to know what is the effect of what time I leave on how fast I get to work, that is a testable question because I can measure something. I can measure what time do I leave my home, and I can measure how fast or how long it takes me to get to work, and I can find a relationship between those variables. There's something measurable about it. The second thing is I need a model. And we talked in class about why we need models. They provide a structure to translate between what we want to know and what is actually measurable. If you recall in class, we talked about how a model mediates between observation and reality. Most of the time we cannot actually measure things we want to know. For example, we looked at planetary transit, and we want to know, is there a planet passing in front of the star? We can't actually see that planet, so we have a model that lets us infer the presence of a planet by looking at the dip in the brightness of the star. This is a model. This is not a planet. This is a dip in the brightness of a star. It's a model that lets us take what we can observe, which is brightness, and infer something about reality, the presence of a planet. So that's an example of a model. Even something as simple as a spring scale involves a model. If you think about it, we're not directly measuring force. We are really measuring a displacement. Right? This is delta x, a displacement. And what I'm hoping is that this spring scale obeys what's called Hooke's law, which is a model of how springs and other elastic stretching, tension, compression objects work. I'm hoping that it fits this model, that the force on the object is directly proportional with some constant to the displacement. What I'm actually measuring, what I'm observing, is a displacement. I'm inferring what the force is. Even a spring scale is a model. We want to think about what uncertainty might result from our model. This typically results in a systematic error, and I talk about that in an earlier video. Review that if you need to. But we can result in several errors just from the way that we structure our model. In this example over here with the spring scale, if I haven't measured this spring constant correctly, then I'm not going to have a proper relationship between displacement and force. I will have a systematic error in my model, and I'm not actually going to be recording the right force for the amount of displacement. So we need to think about that. Third, I should define a procedure. What materials am I going to need? What process am I going to follow? And what approach am I going to take to analyze the data afterward? There should be a plan for that. And the reason we want to plan for it up front is so that we can make sure we don't run into any unexpected issues. If we find out halfway through gathering data that, oops, we really should have been gathering 3 data points for each measurement and averaging them, now we have to go back and start all over again and retake a bunch of measurements to make sure that we did it correctly. So it's really important that we define our procedure in advance and sort of spot check it to make sure, does this make sense? Is this going to actually get us what we want to find? Similar to when we define our model, we want to think about what uncertainty might result from our process. Typically, an error that results from our process is going to be a random error, but sometimes it could be a systematic error if our process is somehow related to a bias or some other type of systematic error. And finally, we need to think about presentation. How am I going to present the data numerically and graphically? What format is best going to convey my point? And on a couple slides, we're going to see how we can choose what graph we get based on our testable question. This is sort of a graphic that's showing you the importance of the question, how do we present our data? There's not just one kind of graph. You are probably most used to this kind of graph of data, a scatter plot. Typically in our introductory science courses, we're looking for the effect of one variable on another variable, and we can plot it as a scatter plot and then look for trends. But there's many other different kinds of graphs. When should we use a column graph? When should we use a bar graph? When should we use a pie graph? It seems a little bit random at first, but we'll find that there are actually some basic rules that we can use to get a pretty good idea of which graph we should select. And this is really going to depend on our testable question. The way in which we phrase our testable question gives us a pretty good idea of what kind of graph we should use. If we have the testable question, what is the effect of blank on blank? This is the kind of testable question that you're probably used to from introductory science courses. Then what we're going to do is measure an independent variable. We're going to measure a dependent variable, and then try to see if there's some effect of the independent variable on the dependent variable. Typically, we plot this as a scatter plot. So if you see these keywords, effect of or correlation between, you're probably looking at a scatter plot. On the other hand, I could phrase my testable question like this. I could phrase something like, what proportion of U.S. energy supply comes from renewable sources? And if I'm talking about what proportion or percentage is a smaller category within a bigger category, for example, renewable sources of energy are a smaller category within total U.S. energy supply, and I want to know something about the proportion. This is a case where I might want to use a pie chart, and a pie chart is going to be able to show this kind of thing a little bit better than most other graphs. I could have a testable question like, what is a typical temperature of a star by spectral class? And spectral class is just a category of star. If I'm sorting things by category or type, and I want to compare different categories or types, then I'm probably talking about a bar or a column graph. And there's another kind of testable question, which is, how has the atmospheric CO2 level changed over time? Keywords here, changed over time. If I'm looking for something that is a general trend, something that is changing over the course of years or months or minutes or seconds, if the x-axis is time, you're probably looking at a line graph. And there are more testable questions than this. There are more types of graphs and charts than this. But these are the four main ones, and I think these four capture a lot of the different kinds of data and experiments that we're going to be wanting to perform. Let's look at some examples. So what is the effect of string length on the period of oscillation of a pendulum? This is a testable question that I posed in an earlier video. I went into Plotly and I made my scatter plot. I have on my x-axis my independent variable, string length, and I have on my y-axis my dependent variable, period of oscillation. And I was able to plot my data points, put my error bars using the standard error, and fit a trend line. Back in Plotly, you'll notice that when I go to my data tables and I click Make a Plot, I have a lot of options. There's all these different types of charts. I told you to select scatter plot for that particular chart, but now we know why. because of the way that I've phrased the testable question, because of the type of experiment that I'm doing, this type of experiment lends itself to a scatter plot to best show our data. Let's take a look at my second testable question that was an example. What proportion of U.S. energy supply comes from renewable sources? And I actually literally Googled this question and looked for some charts on the web, and I found this one from the U.S. Energy Information Administration. And here we have a pie chart that has the total breakdown of U.S. energy, and it gives me a slice of that pie chart which is renewable energy. And this is actually really cool because within that slice, that 9% slice, it actually breaks down what kind of renewable energy makes up that slice over here, that 9% slice. So here's a way of presenting data that has to do with proportion. My third kind of testable question was sorting things by category. There are 7 different spectral classes of stars, and we just call them a class O star, a class B star, class A, so on and so forth. Our sun is right here, a nice yellow star, class G star. And what's important about this graph is that we are organizing things by category. In this particular case, we're using the category of spectral class, but any bar graph or column chart is going to show things by category, and that's what's important here. Spectral class is a category, and I have some information that I can plot. If I have uncertainty in these measurements, I can actually put error bars on a bar graph as well. So error bars are not necessarily limited to a scatter plot. Here is an example graph from my fourth type of testable question, which was looking at change over time. And this is from the IPCC, the International Panel on Climate Change. And we see on the x-axis years before 1950, and on the y-axis carbon dioxide in the atmosphere in parts per million. And you can see the trend over time goes in cycles, and then here, starting around the 1800s or so, we get into a very sharp uptick. And these kinds of graphs are useful to put things in perspective over time. We're looking at trends that occur over, again, any unit of time, seconds, minutes, days, and in this case, hundreds of thousands of years. What I have here for you are 6 sample testable questions. And what I'd like you to do is pause the video and see if you can determine what would be a great graph type for each testable question. Ready, go. Were you able to come up with a graph type for each testable question? I hope so. And you're going to be disappointed because I'm not going to provide the answer key on this one. Next time we meet as a class, what we're going to do is get into groups and compare notes, and we'll see if we have some agreement or disagreement on which type of graph we should use. So be prepared for that discussion next time we meet. Things you should be able to do right now: recognize the elements of a good experimental design and know why they are important. You should be able to explain how the design of an experiment may lead to specific systematic and random errors. I did not talk about systematic and random errors in this video. That was a previous video called Measurement Uncertainty. So go back in Edmodo or back in my YouTube channel to find the video about error. You should be able to pose different kinds of testable questions. Remember that what makes a question testable is the fact that we can measure something. And you should also be able to select an appropriate graph based on the testable question and justify your choice. At this point, I suggest that you practice. Go back to our experimental design process and practice. Form a testable question. Ask yourself, is this something I can actually measure? Is it a testable question like the other example testable questions that have been provided in this video? Think about what model lets you actually measure something and translate it in what you want to know. Practice making a procedure. How would you actually go find out the answer to your testable question? And then practice choosing a way to present your data. Are you going to choose a scatter plot? Are you going to choose a bar graph or column graph? Are you going to choose a pie chart or a line graph based on your testable question? There are an infinite number of testable questions that you could ask, which is why science is so rich and complex and ongoing. So go out there and practice.